Hi everybody. In grading your homework, in grading your homework, this was a common one that I saw that a lot of people were struggling with, or just kind of getting so far, not really knowing what to do. So I wanted to go over it to kind of show you how I would go about solving a problem like this. So basically, it's number 39 from chapter 11. So number 39. You get a y-axis here, and then you get mass 1 moving like this. You get mass 2 moving like this, mass 3 moving like that, and mass 4 moving like that. So those are the masses on the axes. They're giving me an axis, and they're saying, suppose the particles in the preceding problem, that is from this problem, have masses 0.1 kilogram, 0.2 kilograms, 0.3 kilograms, and 0.4 kilograms. So that's all the masses. The velocities are V1 is 2 I hat. I'm going to go with my convention because it just makes more sense to me, is to go with X hat. And then V2 is 3X hat. And then negative 3 y hat. I just like the x and y instead of ij. J would be y hat, so 1.5 y hat for V3, which that makes sense, it's pointing directly down. This one makes sense that it's this because it's pointing kind of off and to the right. And then V4 is pointing at negative 4 x hat. Meters per second, and so those are all the velocities there. And it says for us to, let me grab those velocities really quickly, do it in a bit of a different color here. And then it says calculate the angular momentum of each particle about its origin. Okay, let's do it. So in order to do this, I'm going to, so for part A, I'm going to use the fact that the angular momentum, while it could be I omega, another way to write the angular momentum is the cross product of r and the momentum. And I saw a lot of people in their work actually do the legit cross product, and that is totally fine. There's nothing wrong with doing the legit cross product of something. However, the other way that we could write that, and that would be the magnitude, by the way, the other way we could write the magnitude is the magnitude of the r vector times the magnitude of the momentum multiplied by sine of the angle between those two vectors. So again, that's we've seen this time and time again. That's the angle between those two vectors right there. And the r vector is the angle from your axis of rotation, or basically where you're measuring from, in this case, to where the object is that carries this particular momentum. So that's another way that you can calculate the angular momentum. And I derived this in class a week ago or so. We kind of saw the relationship between this, and that they're basically expressions of the same thing. So to do this, then, I'm going to do L1. So calculate the magnitude of L1. So it's going to be equal to the magnitude of R1 times the momentum. Well, that's going to be M1 V1. So this is and then times sine of theta 1. So let's go ahead and look at that. So here's my axis of rotation right here in the center. R1 is going to be a kind of a vector arrow that goes from the axis of rotation to where object M1 is. So that's going to be R1. And R1, you can clearly tell, is equal to 2, right? So that's equal to 2 right there. So R1 is going to be 2. Remember, all this is magnitude. In order to do the direction, I'm going to use my right-hand rule. So we'll see what that looks like in just a moment. And then M1, well, M1 is 0.1, right? 0.1 kilograms that I got from the problem itself. And then times V1, which they give me V1 is 2, and I can clearly see it's moving in the positive x-axis, meters per second like that. So it's going to be 2. And then the angle between these two, I'll do this one in gray, is 90 degrees, right? So, and then sine of 90, and sine of 90 is 1. So this is going to be 0.1 times 2 times 2. I think that's going to be 0.4. I hope this doesn't bite me in the butt. afterward. And then I'm instead of doing just the magnitude, I'm also going to write the direction in just a moment. So that 0.4, the units for angular momentum are kilograms meters squared over seconds. And then to get the direction, I'm going to use my right hand rule. So my fingers my hand's going to go along here like this, and then my fingers are going to curl to the right. So if I took my hand and let it lead, if I put my index finger, and all my fingers out in that direction, but then curled them to the right, my thumb would naturally point into the page. And so typically by convention, out of the page is considered the positive z-axis. And then into the page, that's x, is considered the negative z-axis. So this is going to be pointing into the page, and that's the negative z-axis. So it's actually going to be negative z-hat right here. So that's kind of telling me, so I got that right there. There's my angular momentum there. For the angular momentum for 2, so let's just go ahead and do that. So for, let's do it in a different color. We'll do L2. Again, it's going to be R2, the momentum 2, so it's M2 V2. And then that's magnitude of all that, times sine of theta 2. Now, here's where I'm going to skip over some of the other stuff because I don't really care. Because here's the thing. Here's my R vector. It goes from the axis of rotation to here, right? I could do the Pythagorean theorem, try and figure out what R2 is, blah, 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 and make my life miserable. But look at this. My R vector is pointing in the same direction as my velocity vector. And remember, momentum is equal to mv. So whatever direction the velocity vector is pointing, that's the same direction the momentum vector is going to be pointing. So I can see my momentum points this way, and my R vector points the same way. So what's the angle between these two? Well, it's 0. So the angle, if I put these two together, here's R2 and here's V2, and I put them together, the angle between them is 0. And so if the angle between them is 0, sine of 0, whatever the heck all this nonsense is, sine of 0, well, that's just 0. So all this then, that means the angular momentum here, L2, is just going to be 0. All right, let's try L3. So again, I'll do just the magnitude. It's going to be R3 times the momentum, which is M3 V3, times sine of the angle between them, theta 3. So this is one of the things that I was talking about. Really, truly, my R vector is like this. In fact, I'm gonna kind of let go of this right now, really quickly, just so I can emphasize what's going on here. So my R vector, I'm trying to draw this as best I can, is like this. Ay, ay, ay. There you go. There's my R vector right there. There's R3, and I would need to find out what R3 is. It looks like it's at a destination. It looks like R3. I'm seeing it's like at like 1. So, sorry, -3 to the right, and then 1 up, and that's probably in meters right there. So that's how I could define it, and then I could use Pythagorean theorem to find out how big that is, etc., etc. Then I need to find out this angle, which none of this is really that difficult. I could find that angle, or not to say it's not difficult, but I would need to do some tedious trigonometry in order to find that, and that would give me my angle, and V3 they already gave me, right? Or I could use this idea that I talked about in class, which is this idea of a line of action, right? And you've seen this also in the Pivot Interactive, is using that line of action stuff, because we saw as long as there's no torque acting on an object, the angular momentum stays constant. So that basically means that I could, if I could find the angular momentum of M3 at any point on this line of action of where this mass moves, well, then I could find the angular momentum anywhere. So I know that it's going to stay, that V3 is going to be constant. That's not going to change. There's no torques. Nobody told me in any part of this problem that there's going to be any torque. It's so there's no torques acting on the system here. So that means the momentum and the angular momentum as a result is going to be constant throughout. So I could use that line of action and extrapolate to this point here, right, using the fact that the, so I'm trying to be constant here. So this is still v3. The velocity would still be v3 here. And instead of using this weird angled r3, I'll do this other r3. I'll call this r3 perpendicular, because it's the perpendicular kind of component of R3, right? And now I can find out what this is by basically doing, I'm going to be doing R3 perpendicular multiplied by M3 V3, and then the angle between them is 90 degrees here, right? So that'd be sine of 90, which sine of 90 is just 1. So R3 perpendicular, well, this just made my life so much easier, right? R3 perpendicular, that's just, let's see, this is -2 here. And so at this point, it's between 4, so it's going to be 3, -3, right? But -3 in those brackets there means it's just going to be +3, because it's the absolute value brackets. I'm just taking the magnitude. And then, well, we got the angle is 90 degrees. We got that already. And then V3, they told me, was 1.5. So M3 is, oh, shoot, what was M3? 0.3. Oh, yeah, it's a nice little convention. And then 1.5. So this I am going to need to calculate out. I'm just, sorry, I'm not that clever. 3 times 0.3, 1.5. Times 3 times 0.3, and I get about 1.35. So my angular momentum of 3 is 1.35. Again, kilograms meters squared over seconds. And then using that right-hand rule, my hand starts here, and then my fingers extend outward to the left, and then my fingers are going to curl down, right, using that right-hand rule. And if I do that, my thumb naturally points out of the page or towards myself. So that's the positive, out of the page is the positive z-hat direction. So that's going to be positive 1.35 z-hat. I get that. Let's make it a little, it was really fancy last time. Let's do it like that. Sure, let's make this one fancy as well. And we're going to do the last one, which is L4. And that would be, so magnitude, so that's going to be R4 times the momentum, M4V4, magnitude, sine of theta 4. And here we go. So M4 is over here. Hopefully you can get an idea of what the heck is going to happen here, because I can take basically R4 and point it like this. So here's R4 pointing to the right. Well, V4, which is going to dictate what the linear momentum, direction of the linear momentum is pointing, points to the left. Well, the angle between those two vectors is 180 degrees. So theta is 180 degrees here. And that is helpful to me because I can immediately go, well, I don't care about what any of the other stuff is, right? Because whatever all this stuff is, if theta is 180 degrees, sine of 180 degrees is 0. So this is 0. That means all this is 0. So that means L4 is going to have a 0 vector. It would be the 0 vector, or it would just be equal to 0, magnitude-wise. So really the only momentums I need to worry about are L1 and L3. Those are the only things actually carrying any momentum at all, which helps me with this last part, because it says, what's the total angular momentum of this 4-particle system about the origin? Well, the total momentum is just going to be L1 plus L2 plus L3 plus L4. Just literally add up all the angular momentums. So L2 and L4 are 0 already, so I don't really care about them. But L1 is negative 0.4. I'll forego units for simplicity, z hat, plus 1.35 is L3 z hat. And that's positive. So that means then that the total angular momentum for this whole system, meaning the total angular momentum of this whole particle system is going to be 1.35 plus negative 0.4. I think that's 0.95. And again, now I'll bring back the units. They didn't change. I was just adding two numbers together. The units stay the same. And that's going to be my total angular momentum. So yeah, hope that helped kind of getting practice and doing that, because you're going to see this a lot for when you're doing things like the dart pivot interactive that you guys did, and some other things that you're going to see in terms of conservation of angular momentum and stuff. So sometimes you have to convert between linear momentum and angular momentum and vice versa, back and forth. So hopefully that helped. Thank you guys. All right, bye-bye.